Hi, welcome to another lecture on Calculus 2. Today's topic is calculus with parametric curves. So what we want to do is to graph and analyze parametric curves that could be given to us as x is a function of t and y is some function of t. The issue is almost half of calculus. So you see I've listed quite a few topics here that occupies perhaps several weeks of lectures. So I'm going to select a few items that I have marked here and talk about them, and hopefully you think about the rest of them. In general, the topics divide into two categories. One is pre-calculus topics that don't need any differentiation or integration, and calculus topics is what you start to learn in calculus. So pre-calculus topics was the issue of domain and range, the issue of intercepts, intersection of our curve with any curve of interest. Typical items are intersection with x-axis, y-axis, any asymptote you might have, and self-intercept. Of these items, item that is new is self-intersection, so I'm going to talk about that a little bit. Next, you might remember that the issue of symmetry was important, and finding the asymptotes of your graphs were important topics, but we are not going to talk about it today. Among calculus topics, of course, the primary thing is what's the derivative of y with respect to x. Even though in most circumstances y is not a function of x, but locally it is, and we can think about these derivatives in the same sense that we had in calculus 1. You're going to perhaps come across issues of intervals of increase and decrease, where the tangent line might be horizontal, where the tangent line might be vertical. Finding maximum and minimum, typically when y is considered versus x, that is locally y is a function of x, where is the maximum, where is the minimum, and vice versa if you consider x versus y. Next topic will be second derivative, some rather new looking formula here. These primes indicate derivative with respect to t, and d2y dx2 happens to have such a formulation. Of course, that feeds into the issue of concavity. Where is the curve concave up and where is it concave down? Depends on the sign of this quantity. Next comes up issue of what's the length of a curve, what's the area under a curve, and all those topics. As you notice, it's a pretty tall order of variety of things, so let's limit ourselves to a few things that we can do within one or two lectures. Issue number one is what is meant by self-intercept or self-intersection. Well, if you draw a wiggly curve, you notice this issue. The curve is intersecting itself, so it has a self-intercept. So self-intersection or self-intercept is an issue. Let's practice this thing in the context of one example. Suppose x is given to me as a function of t, and that is t squared, and y is given to me as t cubed minus 3t. So what we want to find out is to find intersection of this curve with itself. Okay, it would be straightforward to find the intersection with the x-axis and y-axis and so on. You set corresponding variable to 0 and solve it. But how would you figure out intersection with itself? What does that even mean? So we said we are animating a certain curve. As time passes on, we are on a certain trajectory, and perhaps maybe we come around and then crisscross with the path that we already had. So when we were going in this direction, at some point we have arrived at this point T1, and then we go around the so we have come here at some time T1, and then we go around and come to same point at some time T2. And of course T1 and T2 are different. At some later time we are coming to that point, and that is where we have an intersection. It could happen that the issue would be more complicated. You could go on a curve and continue traveling on the same path that you had before. But let's put that issue aside and let's just concentrate on the issue of intersection at one point. So T1 and T2 are two different times at which we have the same coordinate. So that means at some T1 we have some location which is T1 squared, and the y is T1 cubed minus 3T1. And at time T2 we have exact same coordinates. So this is same as T2 squared, and this is same as T2 cubed minus 3T2. So what I want to do is to solve this system of equation for T1 and T2 with the provision that the two answers that I am looking for has to be different from each other. Of course, if you let T1 and T2 be the same, well, any number will be a solution. That is not of any interest, does not indicate intersection. Well, every problem kind of different, and then you have to kind of use your reasoning. So for example, here in the second equation, I can say let's factor T1. So T1 squared minus 3 will be T2 squared times T2 times T2 squared minus 3. Okay, with the assumption of T1 and T2 being different quantities, the only way this equation can be true is that the quantity you are multiplying with has to be 0. Okay, T1 and T2 squares are the same quantities, so this quantity times T1 cannot be equal to T2 times the same quantity unless this quantity is 0. Okay, so that's a crucial observation here. So when we set them equal to 0, we say T1 squared minus 3 is equal to 0. Well, that gives us two roots is plus or minus radical 3. And the same thing applies to the other one. That also tells us T2 is plus or minus radical 3. So the only way we can keep these two different from each other, we can have either T1 to be radical 3 and T2 to be minus radical 3, or the other way around. If T1 is minus radical 3, then T2 is plus radical 3. So one of these two options should be applicable to us. Now, well, if that's the case, what is x and what is the y? So let's go ahead and pick this one and say this tells us that x, well, T1 squared is 3, and y, well, y is coming out of this formula, which is going to be 0 times whatever you had chosen, so that will be 0. Now you notice that if you had chosen the other one, you would get the same things. X is equal to, again, square of this one is 3, and that one, either of them, you place it in the second equation, you get y is equal to 0. So what we have here is the self-intersection happens at this particular point. Okay, that was item 1. Item 2, the question is, well, in what manner does this thing intersect itself? One primary interest could be find the tangent lines at self-intersection. So what are we referring to? So if you have a curve that has one of these loops in it, what happens is that, well, when you are traveling in one direction, you have one tangent line. When you come around and travel to this point, then at a later time you have a second tangent line passing through that point. So this is a situation that's completely different from calculus 1. In calculus 1, we had very plain event. You had a curve, you had a point on that curve, and on that point you have, well, just one tangent line. There would be no reason to suspect there will be something else. But now we are not looking at functions anymore. We are looking at the graphs of relations, and these graphs can self-intersect and create complicated pictures. And at the same point, you can have multiple tangent lines. Well, how did you find the tangent line back in calculus 1? Everything depended on the derivative. Derivative of y with respect to x gave us the slope of the tangent line, and we need that here. But what's the issue? The issue is, well, y is not given in terms of x, or x is not given in terms of y. So how do I differentiate one with respect to the other one? And here comes our next topic of interest. How do I actually differentiate? How do you find derivative of y with respect to x? So two things are crucial here. One is the chain rule, and the other one is that in a locality, we are going to consider y as a function of x in order to be able to apply the concepts that we had from calculus 1. So in calculus 1, you remember, if you wanted to differentiate a function with respect to a derivative, so for example, suppose I want to find derivative of y with respect to t. Well, I can apply the chain rule and say this is derivative of y with respect to x times derivative of x with respect to t. So we had the chain rule, and we are applying it here with a slight grain of salt here, that we are taking y to be a function of x locally for us to be able to do this. Well, what does this tell us? This tells us that dy dx is, I take this quantity divided by this quantity, so it's dy dt and divided by dx dt. Now this writing is going to be quite substantial, and later on gets a bit even worse. So I need a little bit of shorthand to be able to handle this. So we are going to, in this section, we are going to use the following convention, that y prime means derivative with respect to t, and x prime also means derivative with respect to t. So that's now we are using just as a definition, so that our writing wouldn't get so out of hand. So again, going back to the to the equation that we had for this curve, what did we have? We had x was t squared, and y was t cubed minus 3t. So what's x prime? Means derivative with respect to t, this is 2t. What's y prime? Y prime is 3t squared minus 3. What is dy dx? Dy dx is what we said here is y prime over x prime, which is 3t squared minus 3 over 2t. Well, if we are looking at the intersection and we want to find out what's happening at that intersection, well, we need the slope, and to find the slope I need to have my parameter. Well, parameters, I have two values for this parameter, plus radical 3 and minus radical 3. So dy dx, which is going to be slope of tangent line, is simply is going to be this expression at t is equal to plus or minus radical 3. Okay, dy dx is the slope of tangent line at plus or minus radical 3. I just put it here, so it becomes 3 times plus or minus radical 3 squared minus 3 divided by twice times plus or minus radical 3. So that is going to be radical 3 squared, of course, is just 3 times another 3 becomes 9 minus 3 over plus or minus 2 radical 3, and that becomes 6 over plus or minus 2 radical 3, and that's of course 3 divided by this number, and out comes again plus or minus radical 3. By coincidence we got this, so that is our final value. Slope is plus or minus radical 3. What are the coordinates? We said coordinate x is, intersection point is x is 3 and x is 3 and y is 0. So how do we write the equation of tangent line? Well, in this case, two tangent lines, y minus y of a given point is equal to the slope, either of these two numbers, times x minus the x of the point. So we simplify this thing, and y is equal to plus or minus radical 3 times x minus 3. This is the set of tangent lines that happen at the point of self-intersection. So just to have an idea, x is say 3 here, radical 3, tangent being radical 3. What does that mean? Means you are going at 60 degrees, is that right? At 60 degrees this is going, because tangent of 60 degrees is radical 3. So whatever that curve is, it crosses this point on the x-axis. At that point it makes this 60-degree angle, and then it goes about and does whatever else it has to do. So let's see, we used these two time values, radical 3 and minus radical 3, and they are giving us these two tangent lines. Let's specify that, for example, this one happened when t became positive radical 3, and the other one happened when, that is at that point, at that crossing point, t was minus radical 3. Okay, so that was one more thing we learned, how to take the derivative and how to analyze its crucial fact. Let's repeat ourselves what we learned here. Dy dx, here's a short formula to keep in mind. Dy dx for a parametric curve is going to be calculated like this. Well, next question we might be asked, at what points does the curve have a horizontal tangent line? Well, this is a standard staple from Calculus 1. Horizontal tangent line signals for us that one of these three things has happened. Either you have reached a maximum or a minimum, and occasionally in rare circumstances perhaps something like this happened. These are possibilities too, not that common, but they do happen. So you can have this kind of concavity flipping, and etc. So over there we had the issue of the maximum, minimum, and so on. Sometimes this was classified under neither, but significance of tangent line was to signal for us that perhaps something important has happened. Well, what was the approach to that? The approach to that was that dy dx was 0. Okay, that was the slope for a smooth function. Dy dx has to be 0. Well, now dy dx is y prime over x prime. And for this, for a fraction to be 0, numerator has to be 0 and denominator has to stay away from 0. Of course, denominator better stay away from 0 because you want to divide by 0. So in our situation, again, let's remember that x was t squared and y was what is it, t cubed minus 3t. We are looking at the same curve. So the recipe for this is y prime is equal to 0, so 3t squared minus 3 is equal to 0, which tells us t squared is equal to 1, which tells us t is equal to plus or minus 1, which tells us x is 1 and y, if I used 1, I get 1 minus 3 is minus 2, and if I use minus 1, I get minus 1 plus 3, and that's plus 2. So now that becomes minus 1 plus 2. To make it clear, t1, x was 1 and minus 2. Is that right? Let me check. Okay, t1, x is 1, y is minus 2, or t is minus 1, x is again 1, y is plus 2. What does that signify? One big thing that signifies is that definitely we are not looking at the function. Y is not a function of x, because look, same x, different y's. So here what we have discovered here is that x equal to 1. Either you go 2 up or 2 down. Here we have a horizontal tangent line. Here you have another horizontal tangent line. And of course we had at 3, 0, we had a self-cross. So we have discovered this one here. We have a self-cross here. We have horizontal tangent line here, horizontal tangent line here. So this one was at this one was t equal to 1, x equal to 1, y is equal to minus 2. This one was t equals to minus 1, x is 1, y is 2. And also you remember that the blue one going this direction was at t equal to minus 3. So t equal to minus 3, and here is t is equal to plus, excuse me, t was what, minus radical 3, is that right? T is equal to minus radical 3, and t is equal to plus radical 3. So what we have here, t equal to minus radical 3, we are crossing over this significant point here, go up. T minus 1 looks like we are making it up here, and then what? somehow at t equal to 1 we are reaching down here and then continuing over this. So it kind of looks like perhaps there's a loop, but let's go ahead and discover more. What else can we ask? At what point does the curve has a vertical tangent line? So at what points does the curve have vertical tangent line? So of course this is a situation where we say, well, so again x is t squared, y is same t cubed minus 3t. We're looking at the same thing. Vertical tangent line translates to what? What do you think? Vertical tangent line translates to x prime being 0, and we want to make sure we don't have a 0 or 0. So when x prime is 0, this ratio tends to infinity, which is signifying that the line is vertical. Vertical lines don't have a slope, or their slope is infinity, and one way to signal that is your denominator is 0. So in this case, so what is our x prime? X prime is of course 2t, and as before y prime was 3t squared minus 3t. Setting x prime equal to 0 gives us very easy t is equal to 0, which when you place it back here gives us x is equal to 0, y is equal to 0. So what is it that is so important about this? At this point we have a vertical tangent line. So if I go back here, x0, y0, t0, all of them boil down to this point here. This point, x0 and y0 are 0, t is also 0, and at this point we have a vertical tangent line. So our guess was correct, that this most likely what's happening is that this is coming, turning here, turning here, turning here, and coming and going in that direction. So kind of looking like the letter alpha. That's what our curve is. Now let's go ahead and confirm something. This one looks like a maximum. Is it a maximum? We had the first derivative test in calculus 1 and such styles of testing to see if something is a maximum or minimum, or perhaps neither. So let's go ahead and open that can and see where are the maximum minimums, where are the intervals of increase and decrease, and so on. So we are we looked at the issue of what the derivative is. We looked at the horizontal and vertical tangent lines. We want to look at issue of intervals of increase and decrease, maximum, minimum, and here maximum, minimum. One question is, which way are you looking at the function? Are you looking at y versus x or x versus y? Let's go ahead and investigate that further. Okay, find intervals of increase and decrease. Notice again we have a complication here. Like this graph obviously is not the graph of a function, because it doesn't pass the vertical line test in a very loud way. We can say this is not a function because it has a point up there and point down there. For the same x, we have different y's, and it looks very likely that it doesn't have, it's not a function the other way either. So we have to extend our point of view and be a bit more. So when we talk about finds interval of increase and decrease, not as a function, because suppose you consider this this interval here. What do you want to say the curve is behaving? Well, here, if you look at this little piece, it's going down. If you look at this little piece, it's going up. So everywhere, whatever this thing is, it has both up movement and down movement, because it's really made out of several pieces. So what's the way to look at it? One way to look at this thing is as a function of t. Okay, as a function of t, are we going up or down, and so on. So it's not, it doesn't make good sense to say as a function of x. On the other hand, reversing our point of view is that in this neighborhood, this point deserves to be called the maximum point. Okay, this, compared to the neighbors, this is the highest point. Compared to the neighbors, this is the lowest point. So when I look at y as a function of x, by focusing on this neighborhood, this is a maximum. Focusing on this neighborhood, this is a minimum. Looking at x as a function of y, again, this is not a function, but if I restrict myself to this locality, obviously that is the minimum of x as a function of y, and so on. So a bit perhaps complicated, but getting into too much detail of it also not appropriate for our class. So find intervals of increase and decrease. So I say, well, dy dx, as we had it, was, well, we said it's y prime over x prime, and that is 3t squared minus 3 over 2t. So if this thing is positive, in that locality, y increases when x increases. If this quantity is negative, y decreases when x increases. Okay, it is with respect to that local neighborhood that we're making this statement with respect to a particular value of t. Like at any given t, we are on a specific point of this curve, and with vicinity of that point, we are making this a statement not with respect to x. Okay, so after that lengthy talk, we come back to the issue of well, when is this thing positive, when is it negative? This is going to take us back to pre-calculus and when we had to do solution of inequalities. So we had something called the sign chart. If you remember, we had a sign chart that exactly does this. When is this thing positive, when is it zero, when is it negative, and so on. How do you handle sign chart? You factor pieces that you have, set equal to 0. So we have done this thing already. If you have numerator and denominator, you do this thing for both of them. So I see that roots of numerator are plus or minus 1. Roots of denominator is just 0. Then I make a table. Table top row is your variable axis. Your variable is now t-axis. Again, this is not x, it's the t-axis. We have a bunch of numbers here, minus 1, 0, and plus 1. Each of them comes from some factor. Let me remind you, 3t squared minus 3, of course, factors at 3 times t squared minus 1, which factors at t plus 1 times t minus 1. So we factor all of the ingredients, all of numerator and denominator. In numerator I have t plus 1. Also I have t minus 1. Factor of 3 doesn't change sign of anything, so I can put it aside. In the denominator I have t. Again, I put the 2 aside because it doesn't change anything. So I make a row for each of these factors. Factor t plus 1 becomes 0 at minus 1. So I draw a line here, put a 0 here, and say if t is any number less than minus 1, meaning from minus 1 all the way to minus infinity, t plus 1 for any of the numbers from here to here is a negative quantity. After that, after t is larger than minus 1, this quantity is positive. So I expect to have some cells forming here. I draw my cells and I say in this cell t plus 1 is positive, in this cell is positive, in this cell is positive, all the way to plus infinity. That's the story. For t minus 1, the critical point is plus 1. At that point it becomes 0. At all the values prior to that, the sign of t minus 1 is negative, and after that it is positive. T itself, of course, at 0 it's 0. For all points here this is negative. All points afterwards is positive. The expression that we have is a product or ratio of these things, t plus 1 times t minus 1 over t, and I have of course a factor of 3 and 2 here that doesn't change anything. What does that say? That says this quantity is a product or ratio of these things. So if I have 3 negatives, if I multiply and divide them, of course I get negative. Here 2 negatives, 1 positive, of course I get positive. Here 2 positives, 1 negative, I get negative, and here I get positive. At t equal to minus 1 I get 0. At t equal to plus 1 also I get 0. At t equal to 0, since I'm dividing by that quantity, I am dividing a number by 0, I'll get infinity. Infinity can be positive or negative, so it can be plus infinity and negative infinity for us. So that's the sign chart from pre-calculus. What do we get out of that? What we get is that the curve is going to be showing y is going to be decreasing versus x. This means decreasing. So let's write decreasing. For this set of numbers from minus infinity to minus 1, that curve shows a decrease. Here is going to show an increasing behavior. Here is going to show a decreasing behavior. Again, an increasing behavior. So intervals of increase and decrease, intervals of say decrease first. It's crucial in terms of parameter t. Not x, in terms of parameter t. In terms of decrease from minus infinity to minus 1, and then again from 0 to 1. Let's go, before we go any further, see what happens. Here we are guessing that the rest of this alpha, is this tail is here. T equal to minus infinity must be down here. It starts and it goes up and comes around, and t equal to plus infinity is over there, and this was, you remember, this was t equal to 0. So from here to here, how would you label this curve? as t changes, of course I'm going up, but dy dx in this little piece, dy dx is negative, is that right? So we would have considered this in calculus 1. If this was the only piece of my curve, I would have considered this as a decreasing function. How about here? Well, let's go ahead and look at the rest of this thing. So from 0 to 1, for t going from 0 to 1, we say this is decreasing. So maybe I go ahead and label it in some color that we can tell. Here's a blue. If we had such a curve in calculus 1, we would have called it decreasing. And this one, y versus x in these two pieces are decreasing. If we had y versus x in this piece, it's increasing. Y versus x in this piece, it's increasing, and so on. So that is what we are recovering here. Let's see. This is going to be from -1 to 0, and then from 1 to plus infinity. There is a chance of a bit of a confusion with calculus 1, because in calculus 1, when you had something decreasing and then increasing, you would have a minimum there. But here, look, we have a maximum there. How's that? Well, because when t is moving from minus infinity to plus infinity, in this movement, we are going from right to left. Okay, as t is going from minus infinity to plus infinity, for half of that road, we are making from right to left movement. So what would have been considered a minimum, now it's going to show up as a maximum. How do we clarify this thing to avoid the possible a pitfall or something? So dy dx, we said that is y prime over x prime. If my trajectory is from right to left, x prime will be negative, and a maximum is going to look like minimum, and minimum is going to look like a maximum. So what can I do? I can erase the effect of this opposite movement by taking this and multiplying with an x prime. That is, if I take x prime and multiply it by y prime over x prime, whenever this is negative, that is going to cancel it and make it to go from left to right. When it is positive, well, this is also positive, and it's not going to influence anything. So now, when we are looking for maximum and minimum point, your sign chart should only include y prime for finding max or min of y as a function of x. Again, with that grain of salt, that is not a function, but locally we can always make it be a function of x. For finding maximum min, do a sign chart for y prime. So what is our y prime? Y prime was 3t squared minus 3. Set it equal to 0 as we have done it before, plus or minus 1. Make your table. So t is from minus infinity, minus 1, plus 1, plus infinity. And y prime is 3t squared minus 3. Here it is positive, here it's negative, here it's positive. What does that mean? This means that we are going from positive to negative. Therefore, at this t, an up movement versus a down movement, this has to be a maximum point. And this one, from negative to a positive, going down and then up, this is going to be the minimum. So maximum is going to happen at t equal to minus 1, and that is what we had already. X was 1 and y was what was y? Y was, I forgot, y was t cubed minus 3t. So at minus 1, this becomes plus 2. That agrees with what we had before. At t equal to minus 1, x is 1, y is 2. So that is correctly, our guess was correct, that this is a maximum point, and minimum point at t is equal to plus 1, x is again 1, but y is minus 2, and that is our point down here. Now, after all this, you might say, well, we can use a software and graph this thing quickly and be done with this thing quickly. Yes, we can do that. And if you are in a rush, yes, you can do that. But analyzing it in detail as we have done is crucial, because sometimes we cannot see an object and we have to make predictions about it. In 2D is easy to see. In 3D, you're going to see next semester, it's not easy to see much. And of course, if you go to 4D and 5D and so on, the situation comes just that much more complicated. So it's not a bad idea to get used to arriving at a conclusion by algebra. Algebra is essentially a cane for a blind man in higher dimension. You can draw conclusions even though you cannot see something right away. So do your best. What else were we going to talk about? So let's see. We talked a bit about this one, somewhat about this one. So we talked about y versus x, x versus y. You can also see x versus y. When we say x is equal to t squared, that means down here it looks just like a parabola. This is x equal to t squared down here. Disappeared. And if you analyze it, set derivative of this thing equal to 0, you get t equal to 0, and that's the minimum of x when it's looked at as a function of y. In this locality, x is a function of y, and this is the minimum point of it, just like what we talked about. Let's close this thing by going to the second derivative, an issue of concavity. That's another curveball to deal with. Let's see if we can. Let's go back and see that dy dx, let's dy dx, we said it can be written as dy dt over dx dt. It is good to learn this thing in a more general fashion. I'm going to explain why. D of anything. So anything, let me put a box, let me not use a letter so that I'll be a bit more free later on. This is ddt of whatever you had in mind here, and the denominator is just dx dt. So derivative of something with respect to x is derivative of that thing with respect to t divided by derivative of x with respect to t. Now what am I going to do with this thing? What we are after is a second derivative. You might think that, well, second derivative has a formula just like this. Just take the second derivative, and divide. And that is not even close. So that guess is completely off. So suppose I want to take second derivative of y with respect to x. What can I think about it? I can think about as d dx of dy dx. That's what we know from calculus 1. Second derivative is derivative of the first derivative. Now for a second, I ask you to put this thing in that box. Don't mind what is in it. That box is that box. Don't get sidetracked by what is in it. Derivative with respect to x of that box is derivative with respect to t of that box divided by dx dt. So let's write that. So dx of dy dx is d dt of that quantity. So divided by dx dt. Now, as I said at the beginning, this writing is going to be a little bit of a torture. So let's go ahead and use the prime notation. So you remember dy dx, we showed that by chain rule that is y prime over x prime. And these are all with respect to t. So this is d dt of y prime over x prime over dx dt, whose notation was also just x prime. Now in the numerator, I'll just use the quotient rule, derivative of numerator. There's a y prime there, derivative of it will be y double prime. Derivative of numerator times denominator minus derivative of denominator times numerator divided by denominator squared. And the whole thing, denominator divided by x prime. So when I simplify this thing, I get y double prime x prime minus x prime y, x double prime y prime. 2 powers and 1 power here becomes power 3. That was our achievement for today. d2y dx2 has the following formula: y double prime x prime minus x double prime y prime over x prime cubed. Let's put this thing in a box. Let's practice again. Our favorite example was x was t squared, y was t cubed over t cubed minus 3t. I need everything. X prime easy, 2t. X double prime is just x. X double prime is just 2. Let me that is 2. Y prime is 3t squared minus 3. Y double is 6t. All I have to do is to put these ingredients here. Y double prime is 6t times x prime, which is 2t, minus x double prime is 2, y prime is 3t t squared minus 3. X prime was 2t cubed. Who's this? This is second derivative which we use for concavity and such. Let's clean up. This is 12t squared minus 6t squared plus 6 over 8t cubed. So 6t squared plus 6 over 8t cubed. Divide by 2, we get 3 squared plus 3 over 4t cubed. This is d2, d2y dx2. What do we conclude? Well, suppose I want to know for what t values the curve is concave down or up. So I do a sign chart for this. Sign chart. So I have t-axis from minus infinity to plus infinity. Take a numerator, set it equal to 0. That never becomes 0. 2 squared plus 3 is always positive. This quantity never hits 0 or anything, so it does not influence the sign. How about 4t cubed? 4t cubed at 0, it changes its tune. Before we hit 0, for all these negative values, this is negative, and afterwards it's positive. In between, you're dividing by 0 at that point. So if you're trying to measure concavity, you have a bit of an issue. Overall, second derivative d2y dx2, which is the ratio of these quantities, is negative first and positive later. Do we see that? Let's go back up here. Up to 0. Picture is concave down. After 0, it's concave up. At this point, it changes its tune, but we cannot call it the inflection point because y is not a function of x, and so on. So that's the issue of concavity. Okay, so from the topics of today, we selected a few, and that by itself took us quite a while to go through. So we have to study this topic carefully. I leave the rest of it to you. We are going to have more to say about length and area, but let's keep that for another lecture. Okay, then until next time, good luck and God bless.